No, it's weird. It's definitely weird, but it's not cute. I,
Oh, good question. I guess in the syllabus it says Thursday 9:23, but 9:23 is a Wednesday. Our exams are on Wednesdays. I had originally scheduled them for Thursdays, so that's just a mistake. I'll have to go in and fix that. But that's so they're aligned with the other section, so we'll take ours at the same time as Samoylenko's, Vladimir's section. How much time do we have? I think that's on the. I think I made that an announcement, or it's on the homepage of Canvas and stuff. How about this? I'll make an announcement since we're 1 week out from the exam. Yeah, so it's 6 to 8:30, but it's not. The exam itself is not a 2.5 hour exam, if that makes sense. So it's like a. I want to say we make it to be like an hour, um, or maybe 90 minutes max, and then you have an additional amount of time to take it to account for, I don't know, like technical problems, or just like, who cares if you can solve your problems fast as long as you can get them solved. Um, so don't expect to just be like completely engaged for 2.5 hours. Uh, for those of you that have SSD accommodations for ADHD and things like that, yeah, you'll get double that time. We have a list of people, so don't worry about reaching out. But we'll time and a half or whatever, so you'll get 2.5 hours plus an additional hour and whatever, hour and a half, hour and 15 minutes. Yeah, we'll review on Wednesday of next week for sure. And then we'll give you some guide as far as what's going to be on the exam and stuff. So uh, don't worry. You'll have a very, like, going into the weekend at least, you'll have a very firm idea of what's going to be, where to kind of focus your efforts. Right. So yeah, so an exam in 1 week. So I'm glad you guys are thinking about that now and trying to figure out how to organize your time so you can get ready for that. They're a little bit easier because they're online. So you have open notes and open notebook. But you still want to be well practiced in so that you can get in, and you don't want to end. I guess what I'm saying is you don't want to end up realizing that you're a little bit confused in a problem during the exam. So make sure that you do practice some problems. Okay. So we worked through one of the Rice problems last class, and I emphasized the equilibria stuff because we will be doing that moving forward. Next is acid-base chemistry, I think, which is open notes. Yeah, you can use GChem. Open notes means you can pretty much use everything, just don't talk to anybody else. So, and I'll remind you of the kind of rules on the day of the exam. But open note means like it's basically open world, but like you're the only person left on the planet, so you can use all of the knowledge gathered by humanity. You just can't talk with anybody else, or like go and get a tutor or something to work with you on the exam for obvious reasons, right? The sound is cutting in and out. Is that just the mic?
Not for me.
Okay. Okay, good. All right. Yeah. So we worked this tables out. I call it rice table problems. I really should just call it generalized. It's equilibrium problems. Those problems are crucial for moving forward. There'll definitely be some of those in the exams. If you go into, I don't know if it's on the GChem website, but like in a traditional chemistry textbook, there'll be a lot of like hand-wringing about how to solve the problems using simplifications and stuff. And we ran into a little bit of that. The first problem we solved. I don't know, it's 2020, so problem solving, like being able to punch out algebra and stuff is way less important now because you can just use a software suite to solve, any math problem that you're going to come up with. And so I wouldn't be super concerned with that. I mean, the most intensive problem solving thing you're going to see on there is a quadratic equation. So I don't know, hopefully you remember how to do quadratic equations from like high school algebra, and if not, there's plenty of quadratic solvers online. So it's really the hardest part is just getting it in. Well, hardest part. The only part you have to know how to do is get it in the forms that you can solve with for quadratic. All right, so let's see, what should we work on today? I can't remember if I went over in the videos or not Le Chatelier's principle, but this is an idea that falls right out of the equilibrium constant. So presumably a French guy, Le Chatelier. This is a really like solid principle. I don't know why, but for some reason this in my mind is like just has stuck with me as being important. I don't know if that's actually true. It's certainly important for the next couple of exams. It's a useful way for thinking. I guess the reason I think it's important is because it's such a easy qualitative way to look at Le Chatelier is not in the videos. It's okay. I'll just go over it now. It's a qualitative look at like how chemical equilibria work. So you can see from the Rice tables and those types of problems where you're trying to figure out what the final equilibrium concentrations are. It's a little bit of a pain. Yeah, there's been a learning exercise about it. It's a little bit of a pain to solve. Le Chatelier's principle is like you can derive the qualitative concepts from looking at the equilibrium constant, but it's like a nice qualitative look at how equilibria changes as you sort of tinker with the reaction. I'll explain what I mean by that in more detail. So if we look at a reaction, like this, and let's just do it in normal concentrations. We will have this equilibrium expression we can write for it. And we could ask questions like, the reactions at equilibrium. So that's sort of the starting condition. And then you can say, well, what happens if we knock it out of equilibrium? So what happens? What happens if we change I don't know, like concentrations? Products, reactants. That's probably the most important application of it, but also like volumes, which is really just another way of changing the concentration, and then temperature. So the idea here is that you have a reaction that's at equilibrium, and now you're going to throw it out of equilibrium by changing something. So this should make some sense. So like, let's think about the concentration idea first. If K is equal to some concentration, let's look at a real reaction. Let's say you have, let's look at a real reaction. Let's say you have something like this decomposition reaction. So you've got, and N2O4, which is a gas, and it just spontaneously decomposes into NO2 gas. And we're going to say this reaction is endothermic, so delta H is positive. So we can write out our K expression for this. And we don't have to know exactly what the number is for this, doesn't matter. All right, so it's at equilibrium. Now I add in NO2. So I increase the amount of NO2 inside of the container. Is the reaction still going to be at equilibrium? The answer is no, and this should make sense because we haven't changed the temperature, so we know that K hasn't changed, but I've changed something over here. So if I change just one of the reactants, or either the reactants or the products, or just one of the species involved in the reaction, there's no way for K to not change. And so if you deviate from what K is, you're not really at equilibrium anymore. Now you're calculating Q. But if we want to be like just blunt about what I'm trying to say here, I'm saying that, oops. If we add NO2, how would I phrase that? Not the equilibrium shifts. Does it shift the equilibrium? How would I describe that? Sorry, I'm bringing my hands over like some technical detail. Add NO2, the reaction shifts. We're just going to say the reaction shifts. To form reactants, which in this case is N2O4. So I'm saying if I add in NO2, if I'm starting out at some particular concentration here of NO2 and N2O4 that satisfies our equilibrium expression, if I add in product, the reaction is going to shift this way to forming more reactants. And this should make sense, or you should be able to make sense of this by looking at our equilibrium constant down here, which is kind of where I started. And that's just to say that if I'm increasing, if this number is constant, so this can't change unless we change the temperature, which we're not. If I increase this number at the top, so I increase the concentration of NO2, that's going to take me away from what the K value is. And so the reaction is naturally going to try and find its way back to equilibrium. And so the concentration of NO2 will decrease, and the reaction will shift over to forming N2O4 until we again satisfy the equilibrium expression. So, you know, if we're looking at this like graphically, and let's say that we've got, oops. Let's say that we're over here. So we have reactants, and then over here we have products. If our equilibrium condition puts us right there, if I add in products, I'm basically taking myself away from the equilibrium condition. So I'm here, I'm happy. But now I'm adding in products. So what I've done is I've shifted this reaction, let's see, so I have products, yeah. So now I've shifted it to over here. And so now it needs to re-equilibrate to get back down to here, and it does this by forming more reactants. It's kind of like if you took a marble or something. It's kind of like if you took a marble or something and put it into a bowl. If you pull the marble up on the side and let it go, it's going to return back to that equilibrium point. So this is the same thing. We're kind of putting energy into the system and knocking it out of equilibrium, and then it's going to naturally get back to equilibrium. It's, obviously a little bit more abstract looking than that, but that's essentially what we're talking about. I get a question in the chat box, which is, with the equation, would n change to equation? Would the equation then change to NO2O4 to over NO2? No, yeah, no, don't. I'm not sure. I'm trying to think of why you would flip that. Oh, because now you're thinking it's proceeding in the forward direction. No, you don't flip the equation around. So one of the question was, if we add in NO2 and now the reaction is running backwards. This is a reasonable question. So now the reaction is kind of running backwards. Do I now need to flip N2O4 to go into the numerator, since it's products over reactants, since in some sense now the NO2O4 is the product? And the answer is no. So K is defined for whatever reaction that we've written up here. And when I usually say it's products over reactants, but I guess like if you're being really, if you're paying really close attention, then yeah, we could now say that it's not really products of reactions because you're forming N2O4. But just don't think like that. So K is tied directly to this. We don't change that equation, and we don't change this. If we change it, then we're not really talking about the original K anymore. So that's sort of set in stone. So yeah, I'm getting like way in kind of lost in the details, but the general idea here is that if we come back up here and look at this, so let's look at the first one. So if we add C, then the reaction shifts to form more A and B. That's basically what we're saying. And so if we come down here and look at this, it's sort of useful. This sort of idea is useful, particularly in the opposite direction, but it can be useful in either direction. The kind of the corollary to that you would expect is if we add A and or B, then the reaction shifts to form more C. So yeah, when we get into, like in my mind, I was like, oh, it's going to be really clear when you look at K that this is true. But it's almost easier, I think, to just think about it intuitively, which is this, that, I don't know, like if this thing is perfectly balanced, which is kind of what we're saying in equilibrium, right? You're like balanced right around whatever the exact free energy is that you need, or with the lowest free energy is. So you're sort of at these graphics are helpful, but you're sort of at this minima in this bowl right here. If I offset that, so I kind of add A or B, it's going to be like overly weighted on this side. And so to sort of compensate for that, it can shift the equilibrium. I don't like that terminology, but it can shift things over to forming more C so that it can rebalance. It's kind of like if you think of it as being like two weights balanced across, I think this is called a fulcrum, but balanced across this little triangle here. If things are perfectly balanced, and then I add, let's say, a big chunk over here, if I want this thing to stay balanced, I'm going to have to kind of scoot things around. So maybe I can cut off a piece of this and move it on to the other side. That's essentially all we're saying here. You're kind of throwing things off balance, And so some of the stuff that's on one side just has to be moved over to the other. And it's exactly how you would kind of imagine it to be in a kind of macroscopic situation where things are just balanced across a scale. And so that's all we're saying here. So if you add the short thing, the very short explanation, if you just want to like write it down on a crib sheet, is if I add products to a reaction that's at equilibrium, I form reactants. That's what I'm saying here. And if I add reactants to a reaction that's at equilibrium, then I form products. That's what we're saying here. And you can rationalize that based on K. So if you're getting really deep into this, you can look at K and kind of understand why that's true. Let's see. So I guess another almost like corollary to that is I think where to put this at. Not what I wanted to do. Okay. Yeah, the sort of the other thing that you can think about here is that removing okay, let's see. So we've got this idea that adding products shifts the reaction to form more reactant. Sort of less intuitive is if you remove products, that shifts the reaction to form more products. So like in this case, you've got, it's harder for me to think about in terms of, because you have a gas on one side and a gas on another, but you can imagine that if you had some sort of like let's say you had a selective membrane or like a sieve or something that could remove NO2 as it forms, or let's say it's getting siphoned off into another chemical reaction, that's going to, removal of this in some way is going to shift the equilibrium. It's going to shift the equilibrium to the right. And so again, if we look back at having things perfectly balanced, where we say that this is the products and this is the reactants. If I, let's say, cut off a chunk of the products, so now I've cut off that chunk of products and I've just removed it, so it's no longer part of this system. In order for it to return to equilibrium, some piece of the reactants is going to have to come off and form more products. So I lose a little bit of reactant. And that restores equilibrium. So it's the same idea. Before, we were looking at just like the additive situation where it's like I add more stuff to reactants or add more stuff to products. Now we're just looking at the same thing where it's like, okay, well, I just pulled a chunk off of that. It still has to return to this equilibrium point where everything is perfectly balanced. And that's where we can use this analogy. Let's see. Okay, lots of good questions in the group chat. Oh, good. Weight things helped. Good. I'm glad I thought of that. This is what Q is used for. Yeah, you could use Q for this if you wanted to. So you could imagine like we're not using numbers here, but you could imagine that if you have numbers and you add something and you know the exact amount, you could calculate Q and then say which direction things are going to flow. So Q is definitely related to this. And I encourage you to kind of mess around with the numbers and try and figure that out. Equilibrium point is delta G equals 0. And then, let's see, delta G is equals 0. Yeah, I mean, the equilibrium point is where the free energy is no longer changing. Yeah, so the free energy is equal to 0. Yeah, okay, delta G is equal to 0. Yeah, I'm just restating what you said. Is this related with thermodynamics where everything in disorder tends to order, or is there some other rationale behind this? This is not closely related to thinking about entropy. This is more just, this more has to do with just this number being a constant and wanting to, the system just needing to return to having, to being constant there. I guess I can see how it might look kind of like an entropy thing. It could have an entropy component to it. Is that true? Well, let me think about that. Don't worry about entropy, I guess. We're making things more complicated than they need to be. The reality is just think about it in terms of concentrations, and needing for the concentrations to return to something that satisfies this equation. That's really what's happening here. So if we have concentrations for NO2 and N2O4, they have to satisfy whatever K is equal to for the reaction to be at equilibrium. And so those things will change around. It would be related into the entropy probably, but I'd have to think about it. And I think we're just gonna go down a hole of not particularly useful information at kind of the level we're thinking about this stuff. Okay, so then the corollary of this also holds true, that if I remove reactants, it shifts the reaction to form more reactants. So it shifts it away from the product and forms more reactants. So you can see kind of maybe how this stuff would be useful in like especially if you do like chemical engineering or something. I'm trying to think of an interesting reaction to demonstrate that on. Well, let's see. Yeah, it doesn't matter. We can just look at the Haber process. I was trying to think of something you'd be familiar with, but the only thing I could think of was methamphetamine synthesis, and I don't really care about showing you the structures for it, but I think it's going to make it look more confusing. But yeah, if you're trying to, let's say that you're doing the Haber process and you're trying to form the maximum amount of ammonia here. And so nitrogen is super cheap. If you want to push the reaction all the way to the ammonia side, it's easy. It's kind of easier to, you can think about it in terms of K, where you're like trying to calculate out what happens when I use different values of N2 and H2. But the Le Chatelier's principle is you sort of have the notes on this memorize, which is that if I add reactant, I form products, then I know just kind of instinctively that if I just increase the amount of nitrogen that I have there, so put the partial pressure of nitrogen extremely high, I'm going to form more ammonia. So it's a way to kind of form whatever you want in a reaction. You know, if you're trying to do the opposite, which is minimize the amount of side product, maybe you could control that as well through this. But more often, I think it's used to drive a reaction to completion. Another reaction like, let's see, another reaction where you might see this type of stuff would be, let's say, my degree is in organic chemistry, so I'm constantly thinking organic reactions. But let's say you're doing like a, let's say you're doing this reaction with an esterification. So if you're trying to drive this reaction to completion, one way to do it is to get rid of water as it forms. And there's a bunch of different ways you can do that. So both of these things would result in the formation of more products. Right, so here I could remove it. You could also think about that with ammonia with this Haber process. Like if I just remove the ammonia as it forms in this reaction, then I'll continuously just form more ammonia. So if I have a way for kind of removing the product as it forms, then I can continuously drive the reaction to the right. And so these are kind of things that definitely chemical engineers worry about a lot. And you'll see if you go on to take biochemistry or study anything to do with medicine, that this type of stuff is important there too. Okay, so those are the like, those are the types of things, but these are like the really, I had to look up what limiting factor is. I don't know, is that like a biology term? Somebody asked, how does this play with limiting factors? And the answer is, I'm not familiar with that term. So I'm not sure. Limits reactant. Oh, limiting reagent, I say. Let's see, how does this play with limiting reagent? So the idea of limiting reagent, yeah, very good, Edita. The idea of limiting reagents is restricted to reactions that go to completion. In an equilibrium situation, you don't think about things in terms of limiting reagents. I mean, yeah, I would just say kind of separate those two things out. Yeah, so these are the like really obvious things to change in the reaction that's going to change what happens with the equilibrium. Because to me, at least, it's obvious. Just because K is tied directly to, you know, if you've got some generic reaction, like the one we looked at here, K is obviously tied to the concentrations of the reactions and products. So it doesn't surprise me that tinkering with those is going to change something about how the reaction, it's going to force the reaction to have to return to equilibrium in a very obvious way. Very obvious once you've studied equilibrium constant for a while, but that naturally flows from this idea of K. So the other thing that can affect this, which is also not super surprising, is changes in volume. So here in this reaction, we're looking at NO2 and NO4. So if I have this in like a 1 liter flask and I change that, let's say to a 2 liter flask, we could think like, how does reaction shift? All right, so I don't know what your instinct is around it. My first instinct, I think, when I look at this, if I didn't have experience, is just like nothing would change because I haven't really done anything, right? All I've done is you've kind of diluted the gas in a sense because you've expanded the volume of the flask, but everything is diluted simultaneously. And so this instinct is usually wrong. And we can see that if we look back at our expression for K here. Let me rewrite this reaction. We can see that if we rewrite the, if we look at our expression for K here, the reason that the reaction won't shift, or the reason the reaction will have to shift is because one of our concentrations is changing as a square, and the other is not changing as a square. It's just changing linearly. And so it probably makes more sense to write these out as the partial pressures since we're looking at a volume change.
Oh, you forgot to add 2 to the NO2.
Oh, thank you. So I'm writing these out as the partial pressures now. And so we could rewrite this as, since PV equals nRT, we know that P is going to be equal to nRT over V. So we could rewrite this as this. And now it should, well, maybe, hopefully, become a little bit more obvious why why these things don't change. So if I have this square here, as I change the volume, this number at the top is going to be changing much more rapidly than the number at the bottom. So basically tinkering with the volume of the entire reaction, yes, it changes both of these, but they're not changing proportionally because one of them is going as the square and one of them is going as just completely linearly. So if I double the volume, which I did here, this number here is going to become 2, but this number ultimately here, right, is going to divide it out by 4. And so now these things, the numerator and the denominator are not changing linearly. It's basically what I'm saying. And so that's going to screw with now I guess it's going to screw with the way the concentrations in the reaction of products and reactants are going to be. So we can think about what that's going to be. So if the numerator, if the volume is increasing, and the volume is so if the volume is increasing, that means that this number at the top is getting smaller faster than this number is getting smaller. Is that a good way to say that? The number at the top is going to get smaller, not faster, but like disproportionately, I guess, to the bottom. It's going to be disproportionately smaller compared to the bottom. But in order to accommodate for that, since K is not going to change, we're going to have to form more products. So the reaction is going to have to shift to the right. Like effectively what you've done for this reaction, at least, it's kind of like you've diluted the products out. And so now things have to equilibrate. You guys are obsessed with entropy. Not really, so 2 questions. Does K here change here due to entropy? So K doesn't change at all here. This feels nuanced, but K isn't changing. K is staying the same, and that's what's driving the concentrations to change. So K doesn't change. So this is why I'm kind of trying to be careful about saying like, oh, the equilibrium shifts. The equilibrium constant is the same. The balance between the products and the reactants changes because of that. So it's sort of like the fact that K doesn't change that actually is predictive or drives this, the formation of one or the other, the reactants or the products. So the equilibrium constant K is not changing. The concentrations of the reactants and products are changing, so that they can continue to satisfy this equation up here. That's sort of the whole deal here. So it's like these concentrations here can be anything as long as they satisfy this equation. And since this isn't changing, that's what's sort of dictating all this Le Chatelier, not nonsense, but stuff, you know. How entropy plays a role. Yeah, there's some entropic term here because we're diluting and we're kind of expanding the flask out, but you don't really have to worry about that. I guess you could ask, is the reaction shifting due to entropy here? Yeah, I mean, I guess, yeah, it must be. So I guess to answer your question without kind of just trying to drag down on K, the equilibrium does shift here. The free energy is probably getting thrown off. Let's see. Entropy plays a role. Let's just say that. Is there a more universal way to say which volume shifts? Yeah. Yeah, so probably the more universal way to say it is increasing volume increasing volume shifts the reaction to the side with more moles. So in a kind of a generic reaction like this, doubling the volume would shift the reaction right. I mean, shift the reaction to the left. So you're concerned with the total number of moles on either side of the equation. Here, increasing volume shifts to and it comes back again to this same idea that this part is going to change disproportionately to C. So I have like two terms down here that are changing. So this number is going to shrink faster. And so in order to accommodate the fact that K is constant, I'm going to have to form more C and decrease the amount of A and B I have there. Yeah, so it is situational, but we can't generalize it. This is always true. So it's not like, yeah, I guess I'm glad you guys, I guess, asked that. So it's not like increasing the volume always shifts to form more products. It's very dependent on the number of moles that are involved. And so this is a counterexample here with just a generic A plus B situation where increasing the volume shifts things in the opposite directions. And of course, decreasing volume. So now you're concentrating things. Decreasing volume shifts so this would be the kind of the corollary for that. And yeah, so with gases, With gas, it doesn't matter for this type of stuff, if the reaction's endothermic or exothermic, but we will talk about the ways to when that does matter for Le Chatelier stuff. Yeah, I guess so for gases, we look at like just changing the size of the vessel. That's like a way to dilute. With concentrations, you're typically looking at like diluting it out with like an actual solvent. So you'd go from like 1 liter of solvent to 2 liters of solvent. For solutions. And it's sort of the same idea there, right? So you're just changing the concentrations of everything. The solvent doesn't actually affect the equilibrium expression because we just don't count it in. Like it doesn't enter into the mass action expression. And so it's effectively the same thing as changing the size of the flask for a gas. Let's see. I guess let's end on the idea of what happens with endothermic versus exothermic. When does that matter? Basically, the Le Chatelier's principle is I'm trying to think like what even differentiates it from just saying like what, like just doing straight up calculations looking at Q versus K. I think it's useful in terms of like, you can kind of make a crib sheet where under specific circumstances how a reaction is going to shift to get back to equilibrium without having to kind of go through any kind of calculations. So you could say things like what happens if I add reactants, what happens if I add products, what happens if I didn't decrease or increase the volume. But ultimately, if you forget these notes, you can always derive them if you understand the equilibrium constant. So anything that changes the concentration of reactants or products has the potential to change any change in the concentration of products or reactants will shift the reaction from products to reactants. So I can see why they use this language around the equilibrium. It'll shift the equilibrium, I guess, to products to be more product favorable or to more reactant favorable. And so you just got to watch for things that can change the concentrations. So things like changes in pressure, changes in volume, obviously adding reactants or products all affect sort of how the distribution for products and reactants at equilibrium lies. So in the language, I guess the thing I'm keep kind of trying to be really specific about. So in the book and probably on the GChem website, they'll say it shifts the equilibrium, and that's fine. That's an easier way to say it. I just want to be really clear that shifting the equilibrium, what they're talking about is you're not changing the equilibrium constant. You're shifting the balance between the products and reactants to make sure that it's satisfies the equilibrium expression, which is a much more, when I say it out loud, it's much more obtuse sounding. But it's more specific, I think. So K, I guess the main thing I just want to get at is K doesn't change. You're not changing K when they say shift equilibrium. You're changing the distribution of whatever the products, whatever this expression is. If you've got some generic thing, these things can change. And they always change such they satisfy this constant. This thing is constant. That's sort of the idea here. Yeah, so to relate it back to free energy, which somebody is asking about, yeah, there's a shift. The shift goes back. You're basically headed back towards, you're shifting to lower the free energy back down to its equilibrium point. So you're always, I guess in any system, you're always shifting to lower free energy. It just is a general statement. Okay, ran out of time here. So exothermic versus endothermic, we'll cover that on Monday. That's not particularly challenging. And we'll wrap up any loose ends of stuff. Well, obviously, by Monday, we'll have a really firm idea what's on the exam. So we'll wrap up any loose ends with the material. But the hard stuff for you guys that you don't want to be learning on Monday is how to solve equilibrium concentrations. So using Rice tables, know how to get mass action expressions and that kind of stuff. Yeah. And then obviously you should know all the colligative properties and stuff by Monday as well, but hopefully you've been keeping up with that on some level. But yeah, we'll wrap up. We'll do sort of just like a quick wrap up of thermodynamics. So nothing that's going to be like, it's not going to be like another really, like the equilibrium stuff I feel like is intimidating. It's not going to be anything super intimidating. It'll be, if you know what you're doing, it'll be like a nice little, okay, here's like a little topping for the stuff that I know. And then Wednesday we'll do just review to try and get your nerves calm for the Wednesday night exam. And then, yeah, then we'll start new material. All right. We have class Friday though, right? Yeah, I think we'll probably have class on Friday. We can talk about that on Wednesday. I wasn't planning on canceling class. I'll assign, if we do, for class on Friday, I'll assign some learning exercises or something. Or if we don't need to meet, we don't have to, but more than likely we'll meet. There's plenty of stuff to learn. All right. Anyway, you guys have, oh wait, it's Wednesday. So I'm gonna take a break for 8 minutes and then I'll be back for office hours. All right, let's see. All right. Welcome to office hours. What should we talk about in here? Sorry, my break ran a little bit long. I was responding to some emails and lost track of time.
I had a question about number 35 and 36 on the problem set 1. The first one asked, I'll send it in the chat, said, what type of mixtures lead to a small delta H?
Is it a multiple choice or it's just like straight up?
No, it's just a short answer.
Yeah, I guess it's kind of vague. I think we'll probably normally ask that question as like an in-class question. But yeah, it's asking, like, if you take two solvents, for example, and mix them together, or take a solute and dissolve it in a solvent, what's the expectation around delta H for that? I think probably what they're trying to lead you to. This stuff gets kind of messy sometimes, but for us, I think the answer would be something like mixtures where I'm trying to think about how to phrase this succinctly. Mixtures where I just say mixtures where the components have similar or the same, let's say, have the same intermolecular forces. And the reason for that is that remember, delta H is I guess you could say it's like it's related to bond forming and breaking. And so if the strength of the bonds that you're breaking that are being broken are the same as those being formed.
Okay, that makes sense. So
Yeah.
it wasn't, I guess like I got confused because whenever it said small delta H, I was thinking like it was a little vague because I was like, does that mean like super negative? Because that's technically like a really small number. But I guess, so it's just like 0. Like
yeah, I mean, I guess a
0.
better way to, I thought it was kind of vague too as well. Like, what does a mixture mean? Like, are they talking about like homogeneous mixtures or like nails and sand? So it's not the most well-written technical question, but yeah, they're talking about the magnitude of delta H, not the sign. Yeah, usually when you're talking about delta H or delta G or something, and we say small or big, we're talking about the magnitude.
And then the other one, I just sent the other question I had, but it was like, in what cases is the entropy of mixing a negative value?
Oh yeah, that's an interesting question. So when is delta S mixing is negative? Well, that's a good question. When is that true? So That's the whole question. This is another very like vague question. I'm not sure what I put that I put those homework questions together, but I like cobbled them together from previous years. I'm not sure what we're looking for in that original question, but I think there's a couple of situations where delta S of mixing is negative. I think the common one that you talked about in general chemistry is, let's see, so if you do delta G equals delta H minus T delta S, delta S is generally positive. For mixing. And so if you have some understanding of delta S, this should make sense because you're taking something that's reasonably ordered and you're making it more disordered, which more or less lines up with the sign changes for delta S. This is not true when you have.
Oh, would it be like a gas dissolving because a gas is super has like very high entropy, high
Oh, that's a good
disordering?
example. Yeah, maybe that's what I was about to go on a totally different tangent about it. But yeah, the gas is probably what they're looking for. Perfect. Delta S is generally positive for mixing. Yeah, let's say for gases. Yeah, that's the perfect example. There are other examples that are like way weirder that I was about to get into, and you saved me from that for gases dissolving. And look, I was like, I know they're looking for a very specific thing here. Delta S is generally positive for mixing for gases dissolving in liquid. Yeah, that makes sense. And so that lines up too with what we know about gases, which is that if we cool them, so let's say I have like let's say this is closed container. Strong, it's getting out of control. Yeah, let's do this. All right, so let's say you have like a can of Coke or something, and you've got a tiny amount of headspace at the top. And I've got carbon dioxide there. As this gets cold, you've got some CO2 that's dissolved. But it goes up. So I don't know, like how much you can tell when you're using a can of Coke, or like a can of some sort of soft drink. But when you open it, if it's hot, it tends to have a lot more CO2 in the headspace, and the drink tends to be a little bit flatter. Or hot drinks tend to get flatter faster is another way to say that. And the reason for that is because of this free energy expression up here. So you can see that if delta S is a negative, then you have a situation where you have a negative times the temperature times some negative number here. And so this term becomes positive. And so as you increase temp, the delta G becomes more positive. So if the entropy of mixing, another way to say this is if the entropy of mixing is negative, then that's not favorable for the reaction. And so since entropy depends on temperature, as I increase the temperature, I'll actually disfavor mixing, which is sort of not your typical experience, right? When you have like a salt or something and you're trying to get it dissolved and it won't dissolve in, you heat it, and that helps out with it going into solution. And so it's sort of counterintuitive. But you see this commonly with the most obvious example of this is with gases, where the solubility actually increases as you decrease the temperature. And that falls out of this little delta G equation that we know.
Okay, so like this is like another question on that. So it says for an ideal gas dissolving in a liquid, it only occurs at like low enough temperatures.
Sorry, say that again. For an ideal gas.
Dissolving into a liquid, it says like which of the following are true. So this
Oh,
process only occurs at high enough temperatures that wouldn't be true because it needs to be a lower temperature.
that's right.
Okay, that makes
Yeah.
sense. So is
Yeah.
so the dissolution of a gas is endothermic then.
Dissolution is exothermic, but exothermic. It's confusing because delta H is negative. That's exothermic. The signs don't. Yeah, it's exothermic. So it has to, in order for the reaction, if the entropy is positive, I'm sorry, if the entropy is negative, so that's not favoring it. The only way that the reaction can take place is if it's exothermic, because that's the driving force behind it.
Okay, that makes sense.
Yeah.
Professor, I have a question.
Yep.
So I thought the test was on Thursday from like the website. And I emailed you and the TA also, but
Yeah, I'm missing a
Wednesday
lot of emails. Sorry, go ahead.
sir.
I was just
Wednesday.
mumbling that I keep missing a bunch of emails. I haven't seen a bunch of emails from the students. But go ahead.
Oh, I just sent it this morning, so that could be it too. But I was just trying to clear it up. Wednesday of next week, I also have a test in statics from 6 to 8, and the tests in
Okay.
this class supposed to be from 6 to 8:30 also.
All right. You've already emailed us though. Okay.
Yeah, I
Well,
emailed you this morning, so I just wanted to follow up to make sure like it gets noticed, I guess.
yeah. We'll follow up with you. That's a normal accommodation to make.
Okay.
The conflict of exam times. So we'll fix that. So I'm not sure exactly what we'll do. We'll just give you an earlier exam time or a later exam time or something, or put it on Thursday. I don't know, but yeah, we'll respond to you on that.
All right. Thank you.
Uh-huh.
I have a question about number 16 on problem set 1. It asks, some people describe the heat capacity at a phase transition as being infinite. Do you agree or disagree?
Yeah, this is another one of those like questions that works a lot better in class when people can kind of break out into groups and talk about these things. But it does stipulate kind of an interesting kind of like thought experiment. What they're talking about there is that, when you look at the plots of a heat curve or something, or even if you just, well, I think it's easier probably to look at the plot, but if you look at like how, what do? We do temperature change is the point. Temperature change. Yeah. We do temperature change as a function of heat. So the heat capacity, C sub P, is the slope. Essentially, it's a slope of the line on the heat curve. The line. So here, you've got some finite heat capacity. It tells you, essentially what the heat capacity tells you is how the temperature changes as we add heat to the system. And so you could ask yourself, well, like, if it's flat here, if the temperature isn't changing as I add heat to the system, what does that tell me about the heat capacity during the phase transition? if we're defining, so if heat capacity, one way to think about the definition is heat capacity. It's the increase in temperature as we add heat to the system or a system. Yeah, so what does that say about the heat capacity of the phase transition, though? Is the temperature increasing at all? The answer is no. Does that make sense as far as why people sometimes say it's infinite at that point or infinite during the phase transition?
Yeah, I get it. I just want to know if that was a correct statement.
Oh, okay, good. So if you get that part, yeah, whether you agree with that or not is, I don't know, like a philosophical question almost. It's like, my interpretation of it is like, it really just depends on how precise, I guess, you want to be on how you define the heat capacity. So if the heat capacity is precisely defined as the change in temperature, yeah, I don't know. I just get super heady about the question, but if it's precisely defined as the change in temperature as heat enters the system, if the temperature is not changing, then in the mathematical sense, it's of course infinite. But it's also should obviously be true that like it's not infinite in the sense that you can continue to add heat to the system forever, infinitely, and not see a change in temperature. Does that make sense? Like at the phase transition, this slope is infinite, or C sub P is infinite because of the way that we define C sub P. But heat capacity is really like, in the broader sense, is just like when you're looking at it for, if you think about the system as a whole, eventually the temperature will start changing again. So it's not like an infinite reservoir for heat. It's more like, I guess the way I think about it is like here, C sub P is like, not really well defined. I don't know if that would hold up to like a physical chemist type analysis, but like it just doesn't make sense to talk about heat capacity in the range of a phase transition because you're not changing the temperature at all. I'd have to think about it even more deeply to give like a really hardcore answer. But if you recognize why that people say that it's because C sub P or because the slope is 0, yeah, if that makes sense to you, then I would say it's fine. I just wouldn't worry about it. That's mostly what we were trying to get you to look at. So yeah, so I don't know, like getting like down to like a really deep level on that question and trying to figure out like, is it truly infinite, requires some like really, really careful parsing of what we mean by heat capacity and stuff. And I've never actually gone through the trouble of doing that. We're not going to ask you that on an exam. I'm not sure there's a really, really good answer for it, but we could come up with one if we needed to. But we don't have to, I guess, for the class. Any other questions on this stuff?
Where's the video of you working out number 17 posted? Like the one where it's like the 2 ice cubes, I think.
Oh, I ended up just deleting that. We're just not going to do that one on the exam. So I should just strike that off. I should make an announcement about that. I think we did it in office hours. It was just such a train wreck of problem solving that I was like, it's like this is not pedagogically going to be that useful for them. And then I thought about making another video, but I'm realistically, I'm not going to give you a question like that on exam. I guess I really, honestly, I probably could because it's an online test, but yeah, realistically, we're just not going to do that in the exam.
Okay, thank you.
Yeah, I'm assuming your interest in that problem probably ends at, is it going to be in the exam? if you're more interested in it, we can talk about it more. But yeah, I wouldn't worry about it. Other questions?
The keys are going to be posted like closer to the test, right?
Yeah. Let me tell the TA to post it to those. Let's see. It's just a key for the Unit 1 problem set, right?
And then also I was doing like the I don't know what it was called. There's like another one posted.
Oh, like an old exam?
Yeah. Yeah. It has 18 questions.
Yeah. Okay. I just sent an email to the TA to post those. So. But yeah, we'll post those sooner rather than later. And then you can go back. Yeah, this is a good time to go back and just like make sure that things you felt confident about were actually correct. Other stuff? Did you guys get started on the equilibria stuff yet? Yeah, rice tables are a good thing to work on. Let's see. Once you kind of get good at the rice tables, I feel like they all start to be very similar. But it does take a lot of practice to get good at them. We can come up with the more, well, we've got 20, 30 minutes. We'll see. Let's see how far we get. Let's look actually. Let's look at this one. So we can look at this problem, and if we make it to the end of this problem, we have time, we can see what, we can kind of test what, you know, Le Chatelier's principles out quantitatively. See what happens if we add stuff, you know, like if we recalculate the equilibrium concentrations. After we add a little bit more reagent or something. So yeah, so you've got some reaction here. We're at constant temperature. The equilibrium constant K is equal to 1.6 times 10 to the minus fifth moles per liter. And the starting concentration is just 1 mole of that in a 2-liter flask. So I take 1 mole essentially of this and I put it in a 2-liter flask, and then I let the reaction come to equilibrium. So I start out with 0, I start out with 0 of NO and 0 of Cl2. So this is pretty common, where, you know, you only have access to the reactant, so that's your reaction. So you put those in a flask. Now you're letting the reaction run, and you want to know how much of, you know, the products you form, and then if you know that, you also will know how much of NOCl is left over. So, you know, the full question could be at equilibrium. What are the concentrations of NOCl, NO, and Cl2? Okay, so again, this is like the standard kind of like rice table setup problem or equilibrium problem that you see, where rice tables come in handy. So yeah, what can we do here? So we can start out just writing the mass action expression for this. You know, we could calculate Q for this if we wanted to. So if you want to calculate Q, we would plug in the values. Well, actually, it doesn't really make total sense to calculate Q here because we're starting out with zeros in the numerator. So yeah, so Q here would be weird, right? Because how much NO and how much Cl2 do we start with? 0 and 0. Actually, that's fine because the 0 is in the numerator. You can end up in situations where Q is infinite, and then we run into problems. And in the bottom, we have 2 squared, but that doesn't really matter, so we end up with 0. Does that end up giving us the right answer at least? So if Q is 0, then Q is less than K. So K is equal to a pretty small number, but greater than 0. So Q is still less than K. And so if Q is less than K, what does that tell us? Yeah, that tells us, yeah, okay. I just want to make sure that what I'm concluding from the math actually makes sense in reality. So if Q is less than K, that typically means that you're heavy on Q is less than K. That means that this number needs to get larger. Yeah, okay, we're good. Yeah. So at equilibrium, we expect to see increase in NO and Cl2, and a decrease in NaCl. This should make sense, like, even without doing any math, because the only thing that you have in the flask is the reactant. So if the reaction is going to take place at all, the only thing that can happen is to form products. So you don't necessarily have to calculate Q if you only have reactants or you only have products. It makes more sense to calculate Q if I have some population of this, some population of that, and some population of that. If you only have reactants, or you're only starting out with products, let's say, you know the reaction can only flow in one direction, or nothing happens. But here, it works out. Okay. So anyway, so this is like a kind of a sidestep. You don't necessarily have to do that. The more important expression that we have here is just that K is equal to this. And since we know K is equal to 1.6 times 10 to the minus fifth moles per liter, then we know that whatever the values that we end up with for the concentrations must equal this number. So I use the term constrained, meaning that the concentrations can be a lot of different things, but ultimately they're constrained to this expression. And the starting conditions for this, whatever the concentrations are outside of equilibria, will dictate where we end up. So We have 1 mole in a 2-liter flask, so we're 1 molar. Oh, no, why did I do that? We're a half molar of NaCl. Okay, and then from there, you just want to work it like a normal rice problem. So let me rewrite my expression down here. Everything is a gas. I'm just going to leave that off just to keep things a little cleaner looking. So that's our reaction. And then we want to use this table as a bookkeeping method. So we start out with 0.5 molar NaCl. And 0 of this, and there is 0 of this. So it's, it's literally just where we're starting the reaction out. We have half a molar NaCl. It's not at equilibrium. That's what the initial thing is saying. It's not at equilibrium. But now we want to figure out what happens at equilibrium. And so that's when we look at the change. We say, okay, it's not at equilibrium, but we know that it is going to have to change to get to equilibrium. We don't know how much it's going to have to change. So we have to define some sort of variable here. And so we'll set the amount of chlorine that we get to plus X. So we know that we're going to form products. We know that as the reaction goes, we're going to form products over here. And so all I'm saying is I don't know exactly how much I'm going to form. I'm just going to define at least the chlorine concentration that I gain as X. What this means for everything else is just that they will change proportionately according to their stoichiometric coefficients. So I don't know, I know that as I form X of Cl2, that means I'm also going to form 2X of NO at the same time. I can't form if I form any amount of this, I have to form twice as much NO. That's what the recipe or the chemical reaction tells me. The stoichiometry fixes that. And that also tells me that where that's going to come from, that material is going to come from the reactants. So I'm going to lose 2 times the amount of NaCl for every amount of Cl2 that I form. And I'm going to form equivalent, like I'm going to lose 2 moles of NaCl for every 2 moles of NO form, right? So these are going to change proportionally, but these are going to change like exactly the same. I'm going to lose 1 mole of this, I'm going to gain 1 mole of that, or I'm going to lose 10 moles of this, I'm going to gain 10 moles of that. And this will be like half. So if I lose 10 moles of this, I'll gain 5 moles of that. That's where I'm just saying that just because that's where those X or the coefficients on those variables come from. And then, so then we can use this to define our equilibrium expressions. We'll say that at equilibrium, we know that the amount of NaCl that we're going to have is going to be 0.5, which is what I started with, minus the amount that I lose, which I'm calling 2X. And the amount of NO that I have is going to be the amount that I started with, which was nothing, plus 2X. And the amount of Cl2 that I have, is going to be 0 plus X. I started with 0 moles of Cl2. Yeah, where did the 0 come from? The 0 is we started out with nothing. Which is common, right? Like if you're going to run a reaction, a lot of times you don't have the product. That's why you're running a reaction. So you would start out with nothing. Okay, but so once you get to this point, it becomes pretty algebraically intensive. And so we want to use this expression. And so we're just going to plug in values though. So like this whole thing here that we did was ultimately to come up with this, right? Like where we made these terms up, or this is something we're given. We made this term up, and then we use that to calculate what would be the equilibrium concentration of it. That's what we're saying here. We're saying that at equilibrium, I know that this number doesn't change because that's our K value. And we know that the concentration of NaCl is not going to be what we started with because it's not at equilibrium yet. And we're going to call the equilibrium value of it this expression. That's what the Rice table allows us to do essentially. And then for NO, we just end up with 2x. Gotta make sure we square that. And then for Cl2, it's just going to be equal to x. So I'm just going to say this again because this is always a kind of a common point of confusion, which is that this number here is not really related to this here. I mean, it's related in the sense that they both come from the coefficient, but like this 2x and x and 2x and stuff, that just falls out of some algebra, which is a separate concept. We could call this x and call this half x and still have the same answer come out of this. Whereas the square on this is hardwired into like the physics of how we're defining the situation. So one is an algebraic thing and the other is like just kind of the way that the physics of equilibrium work. Okay, but now we just want to solve this thing. So these can be a pain in the ass to solve. Here, K is very small. So if K is very small, what does that tell us about how much product we're going to form? So remember, at K equals 1, we'd have 50% product and 50% reactant. If we're below 1, it's going to be reactant favored. If we're above 1, it's going to be product favored. So as K, one way to think about it, I guess, one simple way to kind of think about K is as K approaches, let's see. It's weird to think about K equaling 0. But yeah, I guess as K approaches 0, as K approaches 0, then you don't form any products at all. Right? So if K was equal to 0, you would have no products. As K increases from 0, you start to form more and more products. And then when you actually cross over 1, now you actually have more products than you have reactants. But K is very small, so we're not going to form much in the way of products. So this is whatever x is equal to is going to be kind of a small number. So this is you could solve. Actually, yeah, I don't know exactly how this works out if you try and solve it out brute force with the algebra, but you can make the approximation that whatever amount of product forms is going to be small. So 0.5 times 2x is probably going to be approximately equal to 0.5. So we're going to make that approximation like I did in the first class, but this one's going to actually work better. And then we can combine these terms at the top. Remembering to square the 2, we end up with 4x cubed over 0.5. And so now we can solve. And we could say that whatever the cube root is of that is equal to x. And so we could say x is equal to 1 times 10 to the minus second if we solve that. So X is very small. Relative to 0.5. If you actually go through and subtract it out, like we're about to do, we'll see that it doesn't even really move the concentration of the reactant in any kind of reasonable way. So, so let's go back. So let's think about what we did here. So I calculated X. That's what all this crap was about, right? I used this mass action expression so I could ultimately figure out what X was. You know, what is that number relevant to? That allows us, X here ties back into these expressions up at the top. And so if we remember correctly, or if we recall why what we're writing out the Rice table for, is the Rice table gives us, these are the concentrations of all species at equilibrium. That's what these expressions are. We just don't actually know what X is, so we can't say what it is from the Rice table. That's why we go through this solving process here, is to just figure out what X is. And that allows us to then take these expressions it allows us to take those expressions, and now we can finally express our answer, or we can actually calculate our equilibrium concentrations. So if I want to know what the NaCl concentration is, I know that it's equal to 0.5 minus 2x, because that's what I've defined it as. And my NO concentration is just equal to 2x. My Cl2 concentration is just equal to x. So this tends to cause some confusion for students because, like, this number here, it's like, well, how is that accounted for here? Like, you know, like, where's the 2 at there? I guess I encourage you to kind of think through it, but those numbers are not, those numbers are sort of the 2 out front is sort of already accounted for by the algebra. That's why we said minus 2x. The concentration, which you're defining, these equilibrium concentrations that we're defining here are like unrelated to these coefficients in some sense. Like, I'm just saying that whatever NaCl is, it's just equal to this straight up. So I don't have to worry about what these coefficients are when I'm finally doing this final relationship down here. That doesn't matter. I don't have to worry about it because I already thought of that and I accounted for it right here. So yeah, so now I just go ahead and I plug in my values of x, and I get 0.5 minus 1 times 10 to the minus second. So that is 0.5 minus 0.01, which is 0.49. So this is why we know that our approximation is fine, because like this is a really small fraction of 0.5. It's like almost a rounding error for it. And then for NO, we end up with 2 times 10 to the minus second. And then this one is just equal to 1 times 10 to the minus second. So those are our concentrations. Of the different species in solution. And so these are our equilibrium concentrations. And that's sort of the whole thing here. So we start out with this information. We say, okay, we know NaCl not at equilibrium So this is equal to 0.5 molar. This is equal to 0 molar. This is equal to 0 molar. This is our like starting condition, is we're not at equilibrium. And we want to know what they are at equilibrium. So once the reaction is done, after we've allowed it to sit for sufficient time and it's done, what are our concentrations going to end up being? In order to figure that out, we have these handy tools that you can look up that are tabulated. We can figure it out by looking at our values of K, which is mole per liter. So K essentially tells us, like, K just tells us like how close the reaction comes to completion, I guess, you know? So if you're going to 100% completion, then K is an extremely large number. And if the reaction is not going to completion, like it's at all, it becomes close to 0. And that's what we're seeing here, is that we're really close to 0. Oh yeah, we're past class time. But yeah, here we're really close to 0. And so the expectation that we have when we're really close to 0 is that these values here are going to end up being very small. And this value that we started with, NOCl 0.5, is not going to change very much. And that's exactly what we see. After we run through our calculations, we see that this is equal to 0.549 molar, and that we see like a marginal increase in the concentrations of these things to 2.10 times to the minus second molar, and 1 times 10 to the minus 2 molar. I should just write these out as 0.2 molar, 0.02. Oh, did I screw up? Is this should be 0.409? No, I'm okay. And so you just form a teeny tiny amount of the product in this thing. So all this crap that we do in the middle here, which I think is where people end up getting bogged down with the rice table and all of this stuff, like all of this is ultimately just a way of calculating yield like we used to do with limiting reagents and stuff, right? That's all that is. It's just to get the value of X so that we can just plug it in and figure out what these concentrations are. So I start out with some condition where I'm not at equilibrium, and then I'm figuring out what the concentrations are at equilibrium. And K is like a, you know, it's like a way to kind of map from not at equilibrium to equilibrium. That's all. That's, you know, like the workflow is I'm not at equilibrium. But I can use K to kind of jump between the two. So at equilibrium. But in order to go between those two states of not at equilibrium to equilibrium to figure out the concentrations, I absolutely have to have K. That's the power of this variable, or power of this constant, rather. Anyway, all right. So rice tables take a little bit of work, but if you just work a whole bunch of them, even if you can't quite wrap your head around like the different parts, like why the coefficients, for example, don't enter into this final expression, if you just work enough of them, you can kind of get a feel for what to do and what not to do. But yeah, the key is to just work a lot of them. And this will become more important, kind of understanding it more deeply as we get to the next exam. So, all right, I will see you guys on Friday. Have a good rest of your Wednesday.